Hello, I am Antonino Furnari from the University of Catania, and I'll present Towards Streaming Egocentric Action Anticipation, which is a joint work with Giovanni Maria Farinella. Humans have long dreamed of building machines able to enhance our perception, support us in our daily life, assist us in situations of need, and more in general, improve our abilities to help us achieve more in a fast-paced world. In more practical terms, we can imagine a device looking at the world from our point of view, which is called egocentric vision. As we move and interact with environments and objects, and as we engage in activities, we would turn to our device as a personal assistant to give us directions on where to go, information on how to interact with specific objects, statistics on how we live in our world, and warnings of potentially dangerous activities. An ideal platform to implement such technology can be obtained by equipping a human with a wearable device including a screen to provide feedback and a camera to observe the world from their point of view. Luckily enough, the market now offers many devices with such abilities, which is encouraging research in the field. Among the different tasks that this system should be able to tackle, predicting what the user will do in the future is one of the most important ones to provide meaningful assistance. For instance, think of a worker in a factory equipped with a wearable device. The system could look at what the person is doing and understand next active objects and interactions to give an alert when a potentially dangerous action may be performed. In this context, egocentric action anticipation has recently attracted a lot of attention. The task is defined as follows. Given an input video with an action beginning at time ts, we sample a video clip of length tau-o preceding the beginning of the action by the anticipation time tau-a, for example 1 second. Note that the observation time tau-o is arbitrary while the anticipation time tau-a is strict and cannot be changed. By observing the video, a model should be able to predict the future action in the form of a verb label, for example take, and a noun label, for example plate. Note that the video or the future action is never observed by the model. The action anticipation task is now popular also thanks to challenges organized yearly at major computer vision conferences such as the Epic Workshop Series, which hosts the Anticipation Challenge since 2019. While the timeliness of the predictions is fundamental in this context, current evaluation protocols tend to assume that models' runtime is always negligible, which, as we show, is not accurate. Let us consider the input video of length tau-o, a target anticipation time tau-a, and the future unobserved action beginning at time tau-s. Current evaluations consider an ideal offline scenario in which the model runtime is 0 and the prediction is immediately available as soon as the input video segment is observed. A more realistic case, assuming a non-negligible runtime, would make predictions available later, thus compressing the anticipation time, which would not match the target one. This evaluation scheme is biased when models are to be deployed to the real world. Indeed, models with different runtimes would have different anticipation times, but they would still be evaluated with respect to the ideal anticipation time. Inspired by recent work on streaming perception, we propose to evaluate methods by shifting the observed segment backward so that the effective anticipation time is greater than or equal to the target one. This evaluation scheme can be easily implemented as follows. Let us consider a test example. In order to process the video, we will first need to fill a buffer with tau-o seconds of video content. At this point, the model processes the video and returns a prediction at time tau-o plus tau-r. Similarly, the next prediction will be available at time tau-o plus 2 tau-r and the next one at time tau-o plus 3 tau-r. The next prediction would arrive late, compressing the anticipation time, so it has to be discarded. In order to obtain a prediction in time, we need to sample the input video here, so that a prediction will be available at time tau-o plus 3 tau-r. Note that past evaluation approaches would sample the ideal video segment here instead, which would produce a late prediction. This implementation of the evaluation approach is straightforward. We take the original test annotations and quantize the timestamps using this formula. Then evaluate methods using standard protocols on the target test annotations with quantized timestamps. Under this evaluation scheme, reducing model runtime is key to performance. A straightforward way to reduce runtime and buffer size consists in reducing the input spatial resolution as shown in these diagrams, which report evaluations for an R2+1D network with different spatial input sizes. Reducing input size also affects performance as shown in this figure. We propose a distillation approach which allows us to use a small input size while still retaining good performance. In the proposed knowledge distillation scheme, each training example is obtained by sampling a pair of video clips tau seconds apart from a longer video. The past observation is fed to the student model to extract a spatiotemporal video representation. If the label of the future action is available for this example, the model is trained to predict it using standard cross-entropy. The future observation is fed to a frozen action recognition model, which is used as a teacher. A custom distillation loss is hence used to allow the teacher to guide the learning process of the student. Note that since video pairs can be sampled in an unsupervised way, the last classification step is optional and will only be applied in the case of labeled examples. Since past and future observations are not spatiotemporally aligned, classic regression losses are not optimal. Instead, we design a custom loss which accounts for this misalignment. We first compute a similarity matrix calculating the cosine similarity between pairs of features at all spatiotemporal locations. We compute the mean of the matrix and then minimize the values of the similarity matrix to encourage extraction of relevant semantic content regardless of its spatiotemporal position. We evaluate different state-of-the-art approaches considering both a standard offline evaluation protocol and a streaming one. Our distillation models are based on an R2+1D architecture with a 64x64 input, which is lightweight and optimized for lower input videos. Notably, state-of-the-art models with large runtimes achieve significant performance drops when evaluated following the streaming protocol. The proposed distillation technique allows to greatly improve results at a reduced runtime and high frame rate. Combining the proposed approach and a lightweight LSTM allows to further improve performance. All runtimes have been computed here using a K80 GPU. Similar considerations can be done on EGTA Gates Plus, with models with larger runtimes being penalized in streaming evaluation, distillation techniques being effective, and a combination of the proposed approach and a lightweight LSTM outperforming competitors. We recently extended our study to more models and input size combinations. This diagram shows model performance with respect to effective anticipation time. Triangles highlight methods evaluated according to a standard offline protocol, while circles represent methods evaluated according to the proposed streaming protocol. As can be noted, slower methods experience a large performance drop when evaluated using the streaming protocol. Also, streaming evaluation changes model ranking, as highlighted here, which suggests the relevance of the results obtained with this protocol. We perform two ablations. We first investigate the effect of the amount of data used for training and the proposed knowledge distillation technique. The proposed method regularizes training in two ways. First, it lets the teacher recognition model instruct the student on extracting discriminative features. Second, it makes unlabeled data available for training. We then compare the effect of different distillation losses. This highlights that different distillation losses can be effective while the proposed one is most balanced. Qualitative evaluations show that one of the main advantages of lightweight models is the ability to observe a video segment close to the ideal one, which is fundamental to performance, especially in videos with fast motion. For instance, in the shown example, the proposed approach, second row, correctly predicts the future action open fridge, because the fridge is observed in the video segment, whereas other models with larger runtimes observe a different version of the input video, thus failing to predict the correct action. Note that the input videos are very similar in the first, ideal, and second row proposed method. To conclude, we argue that action anticipation models should be evaluated also considering runtime for practical applications. To this aim, we proposed an evaluation protocol which is easy to implement and allows to evaluate any approach to also consider runtime. Experiments show that the proposed evaluation method allows to obtain results complementary to previous evaluations. Moreover, a simple baseline combined with distillation techniques outperforms state-of-the-art approaches. We hope this investigation will encourage future prediction community to also consider practical implications related to runtime in evaluating methods. That's all. Thank you for your attention, and please visit our web pages if you are interested in works on future predictions from Egocentric Vision.